Welcome to another lesson of grade 11 functions and applications, where today we're looking at another version of the quadratic function, or another way to represent quadratic functions. And specifically, we're looking at the vertex form. So our learning goal is here for us. We are looking to convert between the standard form, which is the version we've been looking at so far, to now the vertex form, which is going to look like this. And now instead of A, B, C, we have A, H, and K. So we're going to look at first how to get such an equation, and we're going to be looking at completing the square. And then we're going to, in future lessons, analyze what those values of A, H, and K are going to represent and how they affect our function. So the first question we're given is that the maximum area of a garden is defined by, or the area of a garden is defined by the function f of w, and we're asked to find the maximum area. So to do that, we need to find the vertex, which gives us the maximum value. And because I have a as negative, I know that my parabola is going to open downwards, so I will actually have a maximum value. So to determine the vertex, how I'm going to do it for this problem is to find the axis of symmetry and use that to determine the x value, or the w value in this case, and substitute into my equation to get the final area, which is going to be the maximum area. So to do that, we have to find the roots first to find the axis of symmetry, which falls in between the two roots. So to factor, I see there is a greatest common factor here, and I'm going to factor out negative w. And we typically want to work with a equals 1, so it's best practice to factor out the negative as well, so that you end up with just the w. So factoring that out, we get negative w and w minus 40. And again, keep in mind when we are distributing this back, we want to get this original equation. So that's why that negative and negative needs to be there, so that we get positive 40. So now the zero product property tells us that the roots of this function are 0 and 40. So now take a moment and try to find the axis of symmetry. So recall that the axis of symmetry is going to fall between the two roots, so you should have got 20. So in other words, if our graph is like this, we will have a root at 0 and at 40, and we already know that it's a downward parabola, so something like this. And I have my maximum, which will fall on the axis of symmetry, which is at, well, w equals 20 in this case, because we're working with w and f of w. So now the vertex we know occurs at w equals 20, and we're going to find the maximum area by just substituting into f of w, and again, use that original function in case you made any errors in your factored form. So using that original equation, we get that the area is equal to 400. Now, the units. So the question was, had just given you the function and said nothing about the units, which could happen. So in that case, we still want to include units, but since we're unsure, we just write W as 20 units, and the f of W, which is our area, will be units squared. So we still want to include those units there, but just as a general term. So now we found that the vertex is at 20 and 400. So I'll label that on my graph here. And now I've given you another function, which is f of w, and it's very similar to the things that we just saw. So I want you to take a moment and think, how does this new function relate to all the work that we just did? Specifically, I'm going to point something out to you, and it'll be this value and this value here. And I hope you realize that this matches my 20 here and my 400 there. So it's essentially the vertex of the function we just were working with. So to see a little bit more of the relation, if you still are not able to see it, let's try expanding. So definitely try this on your own and I'll show you. Here we want to start by expanding the exponent. So w squared minus 40w plus 400. And the reason I did that so fast is because I'm using what I know for perfect squares here. And plus that 400 there. So now let's distribute the negative to get the following. So now you see that these two cancel out. They will equal 0, and I'm left with negative w squared plus 40w, which is actually that same function that we started with over here. So how is this representation now relate relating to the other representation? And this one now is going to be our vertex form. And if you remember what we saw at the beginning, the layout almost is would have reminded you of this one, and it should have because it's the same. And here we see that A, H, and K appearing, and I'll let you wonder about what the connections here could be. So, we'll see that a little bit more in our future lessons, but today I'm going to show you how we even get to such an equation from the function we started with. And we're essentially doing the process of completing the square, which is the focus of our lesson today. So, what we do when we complete the square is that we pretty much add an additive identity, which is pretty much the positive or negative of the same value, which will equal to 0, such as 3, positive 3 minus 3 is equal to 0. So we add something like this to our quadratic expression to form a perfect square. And that was pretty much what we saw here. We had that additive identity, negative 400 plus 400, which was added in order to use that negative 400 and make a perfect square here, which was our negative w minus 20 squared. And that 400 remains from the additive property because we can't just get rid of it, so it just remains there. And so I have a little definition here for additive identity property, which is pretty much two values that when you add them, they will equal to 0. And when you add them to any equation, it will not change the results because adding 0 to any equation does not change the value. So now let's look at this example where we are given y equals x squared plus 6x plus 5. And I already gave you the algebraic tiles here. So again, our goal is to complete the square. And if we try to move these 5 squares here to over here, we see that it does not complete our square. We actually need 9 tiles to complete the square, but we only have 5. So can we just add 4 more tiles here? And I hope you get that no, we can't just add values that we randomly want because it's going to change the value. It won't be this anymore. So my next question is then, how can we use the additive property of what we just saw to add the 4 tiles without changing the value of our original expression? Well, we would do that by adding that extra 4, which I've shown you with a different color, but also adding the negative of each. So then we have plus 4 minus 4, which fulfills our 0 identity, 0 property identity. Or sorry, the additive. Okay, so we add the 4 and subtract the 4, which fulfills our additive identity property. And now we see that we have a complete square, and my side length here is x plus 3. And this side is the x, and here we have 1, 2, 3. And same with this side, we have x plus 3, which is what we would expect because it's a square. It's a perfect square. Um, so now, algebraically, we have our original x squared plus 6x plus 5, and we're just going to add 4 and subtract 4 to it. Then we see that we require the positive 4 to complete the square, so I'm just going to bracket that into there so you can see it. So I've added 5 and 4 to create 9, and I keep that negative 4 there. Now, this will become x plus 3 squared, and that minus 4. And that was the same as the area of a square with side lengths x plus 3, which will be x plus 3 squared, and we had that minus 4 there. So we have a complete square with a bit of remainder, which is okay, because now we have our vertex form in the expression f of x is equal to a x minus h squared plus k. So let's look at what those values here are. So a would be our coefficient of this squared bracket, and here it's simply 1. H will be this negative h over here. But keep in mind, it's negative h. So what was I subtracting here to get positive 3? And it would actually be negative 3. And you can try x minus negative 3 will give us x plus 3. And finally, for k, we are just adding k. It's plus k. And so we can see from here, it should be negative 4. So, a question for you now is, will we always get a square when completing the square? In other words, can we apply completing the square to any quadratic expression to be able to write it in vertex form? And as we see now the next bit, you'll be able to see that yes, and I'll actually give you a formula for how you would do it and show you how we get to that formula as well. So now let's look at an example where a is not equal to 1, because in this example we saw a is equal to 1, and it was pretty simple. So what do we do if a is not equal to 1? So here we're given the function y equals negative 2x squared plus 16x plus 1. So here a is negative 2. So we have one extra step that we have to do before we try to complete the square, and our goal is to get that a to equal to 1. So you would be factoring, but only from the first two terms. We only care about the x squared and the x term, and anything else after, we'll just add that as we need. So factoring that negative 2 out, we get x squared minus 8x. And double check that if you multiply and distribute this through, you get negative 2x plus 16, and that plus 1 will just stay there for now. So now we want to complete the square for this binomial, which is x squared minus 8x. And for now, we will ignore that negative 2 and the plus 1. We'll come back to it. So looking at x squared minus 8x, I've also included algebraic tiles for this as well. I think with completing the square, it helps a lot to see it visually. So I have my x squared, and this is the reason why we want to start with that a equals 1, because then I can just have this here. And whatever value for x I have remainder, I'm going to split it into two groups to align it next to that x squared square. Now I have a missing piece here, which I need to complete my square. But you already have these to guide you. So if we complete our square like this, we see that we need to add 16. But again, we can't just add 16, so we also have to subtract 16. So here, using the additive identity property, we have 0 is equal to 16 plus minus 16. And that's what we're going to use to complete the square. And so before I go back and finish completing the square there, a food for thought is, how do we know to add the 16 without the tiles? So here, it's easy to see because I gave you the algebraic tiles, but how would you be able to, if you didn't have these, to figure out what you're adding? So keep in mind that we actually will find this out from our b value, because here, as I was saying, if you have that x squared where a was 1, so we only have one of this square, any value of 8 that is any value of x that is remaining, so here we had negative 8x, is distributed into two groups. In other words, this being b is split into two groups. So b over 2. And then we look at what side length is this square that we added here. And you should get that this is b over 2, and this is b over 2. So in other words, we are adding b over 2 squared. And again, because we have to follow the identity property, we will also subtract b over 2 squared. And if we expand this a little more, it'll be b squared over 4 and b squared minus 4. And we can check that for what we just found because we had b as equal to negative 8. So we have negative 8 over 2 squared, which is inside the bracket, we have negative 4, and it'll just give us that 16. So we are adding and subtracting the half of b squared. And essentially, that's what we have written over here for us. So we using the identity property here, we have added 16 and subtracted 16. And this was the same as, or now we can use that to complete the square. So rewriting just the part of x squared minus 8x plus that 16 minus 16 here. And so the bracket becomes a perfect square. Oh, this should be negative 4. Minus 16, because that's the value that we had still left. And I realize now all of these are plus. They should be negative. Okay, negative. Okay, so now we are using that same value for our completed the square, but remember, that value was from here. So we have to go back and substitute it into our original equation. So we had y equals negative 2, and wherever I had that the x squared minus 8x, I'm going to write all of that there because this was equal to x squared minus 8x. But we just added and subtracted other things to create another representation of it. And I had that plus 1 there. But we're not done. We have to now expand and simplify. So expand that a of negative 2 by distributing into the bracket here. But we do not want to expand that bracket because we worked so hard to just find that perfect square. So that's the only thing you are going to keep. But we can still distribute this to get negative 2 x minus 4 squared. And then distribute that negative 2 to the constant term. So we get negative 2 times negative 16 plus 32, but we also had that 1 left over. So now in vertex form, our original function can be written as negative 2x minus 4 squared plus 33. And so now here we have a is negative 2. We have h is 4 here because remember, it was x minus h, so minus 4, just 4. And k would be 33. So now, we already did this, so it should be a little bit of a practice, but we're going to complete the square for x squared plus bx, so we see the general form of it. So and now I'm not going to show you algebraic tiles, so we're just going to imagine the tiles as we try to solve. So starting with that x squared tile, you have whatever bx values you have, those are going to be your rectangles. So you are going to divide that into two groups to align with the x squared. So imagine you have that x squared there. We're going to have a series of rectangles there and some rectangles here, where these are going to be b over 2. Now, I want to complete the square by adding these 1 pieces in there. So Uh, that smaller square is going to be um, so that smaller square that we are trying to fill, maybe let me highlight it. So that pink square there is going to be our ones, and it has a side length of b over 2. But we want to add the area of it, so we need to actually add b over 2 squared. And that will be all of my small pieces in there. So with the additive identity property, we're actually adding b over 2 squared and subtracting b over 2 squared. Then, and I'm going to do an additional step here where I'm going to simplify with the exponent to write b squared over 4 minus b squared over 4. And the minus here is outside the bracket, so you have to distribute the exponent first to get b squared over 4 and keep the negative there. And then that holds for our additive identity property. And now, completing the square, we have here, and this you should know from perfect squares, that this would be b over 2. And whatever we have left is that negative b squared minus 4. So here I have the negative here, so you didn't need to rewrite it. And that would be our general formula for completing the square for a quadratic function with a equal to 1. So here I have those same steps for you just written out so you can kind of follow along. And my follow-up question or exercise for you is to try to expand this now and see that you will actually end up with that vertex form. So you're pretty much doing this backwards. And you can even verify from here that this expanded will give us this. And here we have this A that's distributed through and then so on. Continue and you'll be able to verify that. And here I just have now that what we just did as a official definition for you for standard form to vertex form when A is equal to 1. So when you have a quadratic function in standard form with x squared plus bx plus c, so A is 1, you can write it as vertex form like this. And now consider, what is the significance of A in the vertex form? Does it change? Does A change when you change from vertex form to standard form? Or is it that same A value? And keep in mind, we've been using A to determine the upward or downward motion of our parabola, and as well as other aspects of the graph. So are those different? Why or why not? This example is different from the ones we've seen so far because here we have that b is actually a fraction. But we're going to see that we can actually still complete the square and we'll use the same, we can use the same formula we just saw. So here, to complete the square, we have to add b, half of b squared. But b here being 3 over 2, b squared will be half of 3 over 2 or 3 over 4. So to complete the square, we have to add the square of that, which will be 9 over 16. So we add 9 over 16 and subtract 9 over 16. So now, just writing that back into our equation here, we can complete the square. Oh, this should be 2. By writing here 9 over 16. And this first part is going to be our perfect square. And if you remember from perfect square, we just use that b value. So it'll be x plus 3 over 2 squared. And we had that negative 9 over 16 left over. And we can just confirm here, b was 3 over 2. And for b over 2, we got 3 over 4. And then we got 9. And for A here, 16 there. Okay. And we're subtracting that, so that's why we get that negative 9 over 16. So, just to wrap up our key idea here, so any quadratic function in standard form with a whether it's a or a is one or not one can be expressed in vertex form using fractions. So not decimals, try to stick with fractions as you have to do halves and squares. Um, and one final question for today is, what if our equation is not in standard form? So can you do everything we just did today if your equation is not in standard form? And I hope you answered yes, that by expanding and collecting like terms, you can get your equation in standard form and then be able to use the strategies we learned today. So for today, you're going to be practicing completing the square to convert between standard form and vertex form. And in the future classes, we're going to look a little bit more about vertex form and its graph and applications with vertex form. And I'll see you all next class.